This is part 6 of the series Three-Dimensional Solids, and I'm going to start this part with an example of finding lateral and surface area of a cone. Here we have a basic cone. It has a radius of 9 inches and a height of 14 inches. Now, if you remember from the formula for lateral area of a cone, the lateral area is pi RL, which is the slant height, so we're going to need to find the slant height of this cone. So this dimension here is slant height, and our formula, let's start with our formula. Lateral area is pi RL. Now to find the slant height, that's going to be Pythagorean theorem. This is not a Pythagorean triple, so we're not going to have an easy time of that. So this is 14 squared plus 9 squared. Take the square root of both sides. So slant height is the square root of 14 squared plus 9 squared. And if we put that in our calculator, we get approximately 10.72. I'm going to go ahead and store that in my memory location in my calculator because that's an approximated value and I want to keep all the decimals. Now that's all I have to do here in my lateral area is say this is pi times r, which is 9, times my slant height. And I'm just going to use this approximated value on the screen here, but I will use my formal variable in the actual calculation. And so lateral area is going to be approximately 303.2. So that gives my lateral area. I'm going to go ahead and store that in memory location A, simply because L is already taken up with slant height. And now I can find my surface area. My surface area is lateral area plus big B, and as we know, big B is the area of the base, and so this is approximately 303.2 plus area of the base is the area of a circle. So that's pi r, which is 9 squared. So that's going to give us an approximate value here. And then that value, when we put it into our calculator, is approximately 557.7. And there's our lateral area and our approximate surface area. So altogether, a fairly straightforward example. Let's look at a slightly more complicated example. Now in this example, we have a composite three-dimensional solid, and it's made up of a cone on top of a cylinder, and the cylinder has the same radius as the cone. The height of the cylinder is 7 meters, and we have a slant height given to us that's nice and convenient for the cone, and the radius is 5 meters. Now before we actually get into any calculation, it's important to understand what it is you're trying to find here. Now remember that surface area is the area of all the surfaces that are exposed to the air, if you will. That means that that's all we have to do is the lateral area of this cone. We can ignore the area of the base of the cone because that's covered up by the top base of the cylinder. Then we have to add to the lateral area of the cone the lateral area of the cylinder, and then we add to all that the area of the base of the cylinder. So we have lateral area of the cone, lateral area of the cylinder, and then one base down here. So that adjusts our actual calculation and makes it a little bit easier, actually. So let's start out and say that surface area is the lateral area of the cone plus the lateral area of the cylinder, plus 1 big B. So we have lateral area of the cone plus lateral area of the cylinder plus big B. Now what that comes out to is, remember, lateral area of our cone is pi r slant height plus lateral area of the cylinder is circumference times height. So that's circumference, which is 2 pi r, times the height plus the area of the base, big B, which is pi r squared. Now we'll go ahead and plug in all our values. The first thing we need is the radius, then the slant height, and we're given those two things. Then we need the radius and the height, and we have the height of the cylinder here, and then the radius. So that's all we have to do is plug in. So that's pi 5 times slant height, which is 13, plus 2 pi, and then our radius times the height plus pi times 5 squared. So the radius is 5. Now you could calculate these separately if you wished, and since we wanted to find lateral area first, let's go ahead and do these lateral areas, and then we can get that, and then we'll put in the area of the base. So this is going to be approximately 204.2 plus 219.9 plus 78.5. All right, and that comes out to approximately 502.7. All right, well, again, not a terribly difficult problem. Just you have to make sure that you keep straight all of your variables, and it's really important to have a nice clean work organization. This is going to be key a little bit later on when we get into volume, simply because there's so many calculations and so many intermediate values here that if you don't have your work well organized, it's going to be really hard to track, and it's very easy to make a simple mistake. So with that said, let's go ahead and start investigating volumes of three-dimensional solids. Here we have some representative samples of some of the objects we're going to find the volumes of. And we have a prism, and a pyramid, a cylinder, and a cone. Now the relationships with volume are relatively straightforward. The volume of a pyramid is going to be 1/3 the volume of a prism with the same base area and same height. The same thing goes with a cone and a cylinder. The volume of a cone is 1/3 the volume of a cylinder with the same radius and same height. In class, we demonstrate these relationships by taking some water, filling the pyramid, and pouring it into the prism. And we demonstrate that 3 pyramids will fill this prism. Same thing with a cone. If we fill this cone 3 times with water, it will fill this cylinder, assuming that the radius is the same and the height is the same. Rather than use water here, what I'd like to do is demonstrate this relationship with a little bit more analytical proof. So let's move on to that, and then we'll come back to this display. I have here a cube, and I'm going to break this cube into 3 pyramids. So here's the first pyramid, and you'll notice that the pyramid is kind of a strange looking pyramid. It's sitting off to the side. It's an oblique pyramid, but its vertex is up here in this upper corner. And then I have a second pyramid, and that vertex is in the same place, but it's sitting over here. And then the third pyramid is this one over here. So as you can see, we have 3 pyramids. We have this white one, this yellow one, and this blue one. At least I hope that's yellow and blue. And that makes up the cube. So if I were to add the volumes of all 3 of those pyramids, obviously those would equal the volume of the cube because they're the same shape. So that's what I'm going to demonstrate for you here in just a second. Here we have that same cube made up of 3 pyramids, and we can see that the volume of the cube is going to be length times width times height, or h times h times h, which is h cubed. Now I'm claiming that the volume of a pyramid is 1/3 the area of the base times height. And if we assume that the base is this base, then that will be the volume of our pyramid. Now, as I told you, the cube is made up of 3 of those pyramids. And so I have volume of the cube is 1/3 h squared h. So the base of each one of the pyramids is h times h, which is h squared. And then the height of the pyramid is h again. So it's h times h divided by 3. If I have 3 of those, I add those together. So we have 1/3 h squared h plus 1/3 h squared h plus 1/3 h squared h. Now, of course, each one of these terms has an h squared h in it. If I factor those out, I'm left with 1/3 plus 1/3 plus 1/3. And so we have h squared h times 1/3 plus 1/3 plus 1/3. Well, 1/3 plus 1/3 plus 1/3 is just 1. H squared h is h cubed. H cubed times 1 is h cubed. So there's a slightly more analytical proof of where we get the volume of a pyramid from. So the volume of a pyramid is 1/3 the volume of a cube with the same area base and the same height. Now we can do a similar thing with cylinders and cones, but that proof is a bit more involved and a little bit beyond the scope of this geometry class. So let's just go back to our original plate and we'll continue on from there. Just to reiterate what we've already said, the volume of a pyramid is 1/3 the volume of a prism with the same area base and same height, and the volume of a cone is 1/3 the volume of a cylinder with the same radius and same height, or the same area of the base and same height. Now there's another idea called Cavalier's principle, which we can apply to oblique objects, oblique cylinders, oblique cones, oblique prisms. Now here we have 2 solids, and we've taken this cross-sectional slice of both of those solids. Cavalier's principle states that if you have 2 solids of equal heights, and the cross-sectional areas of those solids are equal at all levels from bottom to top, then those 2 solids have the exact same volume. That means that you would calculate the volume of an oblique prism the same as you would for a right prism. The formulas don't change. Same thing for a pyramid, cylinder, and cone. That wraps things up for this part of the series. In the next part, we'll work several examples of finding volumes of various solids and composite solids. And so I will talk to you in the next video.